Hello everyone. Now we are going to see the circuit for full wave rectification. We have already gone through the half wave rectifier. Now here similar input we are going to consider. Similar input is nothing but a sinusoidal waveform. It's going to draw the input signal. Over here you can see we are covering the diode applications. Now the application is rectification. So this is a V input where vertical axis shows the voltage amplitude and horizontal axis shows the time. So this is the time for positive half cycle and negative half cycle. We are going to go for the T/2 and this is only one cycle we are considering. V input is nothing but Vm sine omega t. This is an AC signal. The conversion of AC to DC that is done by full wave rectifier, that is called as full wave rectification. So here we are going to see the circuit of bridge network, or you can say bridge rectifier. So let me draw that bridge rectifier circuit using diode. So it's a very simple circuit. This side I'm going to draw a square, and in that I'm going to add those components. The main key component is nothing but a diode. So this side is the input side. This is the input side, and over here I'm going to draw that diodes. Here we will connect our load resistance. So one diode will be here, another here, one here, and fourth one here. So let me draw that all the diodes. You can draw like this way. This is this side of phase, so similar phase this side, similar phase this side, and reverse phase this side. This another diode, the similar phase diode this side. So these are total 4 diodes. You can give the name D1, D2, this one is D3, and this is D4. Here we are going to give our load resistance. This is what nothing but our load resistance. These are the input side. I'm not drawn here the transformer part. So this is V input. If you consider this one is for positive half cycle, for the positive this much of half cycle, how the current will move and which diode is going to get on and which diode is going to get off, that we have to see for the positive half cycle, like we have considered for the half wave rectifier. The similar way we will check what will happen to diode, whether diode is it in forward bias or reverse bias. So let us see for the positive half cycle. So this terminal will become positive, this terminal will become negative. So how the current will move? So you can see this diode, the current will move from this side. This diode D2 is going to get in forward bias, and D1 will be act as a reverse bias. So we can simply write D1 is reverse bias and D2 is forward bias. Now how the current will move further? From here, from this side it is not allowed because this one is a negative N part and this is a P part. So N side, cathode side will not allow the current to flow. So current will flow this way and it will go further from D3. D3 is going to get in forward bias and D4 going to be in the reverse bias. So we can write directly that D3 is forward bias and D4 is reverse bias. This is for condition 1, that for positive half cycle. So in the positive half cycle, the current will move in this way, and the whole path, if I draw the whole path, this is the path of that current movement, and it will exit from here. Okay, so this is for positive half cycle. Now when this is happening, we have to measure our output at these two terminals across the load resistance. So as you can see, we consider the diodes are ideal. Diodes are ideal. You can see VD will be 0 for each and every diode. So there is no voltage drop. So for the positive half cycle, we will get V input equal to V output. So whatever V output up to this V maximum level, we are going to get the similar output as input. So if I draw that one, this I'm drawing for the output waveform. For the one cycle only we are working on. So this will similar output, V output equal to V input. Okay, this one what we are going to get to T by 2 times. Now for the second phase, for the negative half cycle, for this one we are working now. Now what will happen, you see, when that is happening, this terminals, now this terminal become positive, this terminal become negative. At that time, you see, current will move like this way. Over here, the diode D4 is going to get on. This one, D3 is going to get off. It will be in reverse bias. So we can write over here that D4 equal to forward bias, while D3 is reverse bias. Now the current will move further from here D4, then it will go in this direction only. It is going in this direction only. You can see in the similar direction. The current is moving further from here. Then after at this point, current will move. So you see, here also current will not able to move because this D2 is reverse bias. So current will move in this way and it will exit from D1. So in our case, this D2 is also reverse bias and D1 is in forward bias. So what will happen? You see, current will exit like this way. It is going in this way, then D2 is forward bias, D4 is forward bias, then after it is moving in this way, and D1 is forward bias, so it is moving in this way and it is going exit in this side. Okay, so this is how once again we will get in the similar direction like a positive half cycle, current moving in the similar direction in the negative half cycle also. So we will get the similar output, but it is inverted. V output equal to inverted V input. So this one what we are getting, because here you see this polarity is not changed. This polarity is not changed. Current is moving in the similar direction in the negative half cycle also. So we are getting this one. This one is inverted one. This one is inverted one. V output is inverted to V input. So this signal, this half cycle is becoming positive one. positive one. So both the signal, both the half cycle in the positive part. So this one is converted DC signal. So this AC is converted to DC. So this is a full wave rectification using this bridge network. This is a bridge network. If these diodes are not ideal, suppose this diode are silicon diode. So each diode will drop a 0.7. So each diode is dropping a 0.7. So at that time, zero point 0.7, once time, suppose you're going for only one half cycle, two diode at a time is going to get on. So here D2 and D3 is on. So we can say it will also consume zero point 0.7 and this also consume 0.7. So total our VDC conversion, when you write the equation for VDC equal to, right, point, this is two times, we are getting two half cycles, so two half cycle in positive part, 0.318 into Vm. But this is for ideal. If you consider the silicon one, it will be, if I multiply this one, it will be 0.636 into Vm minus 2Vk. 2Vk is there because this one is there because we have considered a silicon diode. This will become 0 if the diode is, all the diodes are ideal one. So this is what the equation for VDC, this is for ideal one and this is for practical diode or a silicon diode or a germanium diode, whatever you consider. Okay, so if you consider this one, our DC line will be little bit less, like Vm peak value. This Vm peak value, this one will be Vm minus 2Vk. So this signal will be little bit downside. How much down? That is this value. Like suppose it is a silicon, so 1.4 volt will be removed from Vn and the peak value will be become new peak value, but it will be not greater than Vm. Okay, so this is what all about full wave rectification, and that is particularly circuit of a bridge rectifier. This is a bridge rectifier. Okay, so thank you very much for watching this video. In upcoming video, we are going to see full wave rectification but using center depth